So I'm going to give some, introductions to the chemical looping hydrogen production. So maybe some of us, I think, here can work together to do research in this area. So my objective is to give a useful but brief introduction to this technology. So the outline for the presentation is as follows. First, I give a brief background, and then followed by some fundamental aspect, not all, some fundamental aspect of chemical looping processes, followed by limiting factors, a role of hydrogen towards sustainable development. So what some researchers have thought about it, and then limiting factors to commercialization. Then we look also at the simulation of the chemical looping processes. So there's a lot of article or research paper that have been published in this area in the last 20 years. So I think let me start with the background first. So everybody, I think, is concerned about global warming now. So global warming is a long-term increase of Earth's surface average temperature. So this is due to the pollution, due to the CO2 gas that actually from the industrial production, and from methane. Methane also one of the common cause of greenhouse gas. Up to now, approximately 38 billion tons of CO2 emission produced from fossil fuel and industries. Okay, that is a lot. And also, the largest contributor to this emission is power generation, mainly using coal and gas. At the moment, the concentration already exceeds 420 part per million. So compare this with 280 part per million in 1880s, late pre-industrial era. So again, we also have another term, we call it climate change. So climate change here basically to describe the shift of global weather patterns. So not just the temperature, so these are weather patterns like the cyclones, right? Rainy season and so on and so forth. So this is global weather patterns. Okay, so this one under climate change. So there's a shift of global weather patterns nowadays. And the reason for that, some researchers or scientists believe this is driven by the global warming. So global warming here is the cause of it, and the consequences is the climate change. So I think some of us have seen this trajectory. So this is the profile of CO2 emission from the industrial era. So from 1880s, right, late industrial era. So now it has increased dramatically to above 420 part per million in the air. Okay, so again, this is the one that caused the global temperature increase on Earth. So of course, one of the engineering approach or from engineering perspective is to change our current development to sustainable development. So according to Brundtland 1997, sustainable development is the development that meets the present needs without compromising the ability of future generation to meet their own needs. So the key things about the sustainable development, one of the key things is about distribution of resources. So basically we can think this about two type of generation. So intra-generation or intra-generational equity basically is the fair share of resources among the present generations. Yeah. And then we have also intergenerational equity. So this is the fair share of resources between the present and future generation. So these are the two pillars, okay, within this sustainable development, okay, or what they call it, two criteria. And then how do we view the sustainable development? Okay, first we have the environment that provides us with resource that absorb all the pollutions. So within the environment, we have a social system or society Okay, and then within the society, we have the system within that we call economic system. So this is a strong representation of what we call it sustainable development. So economy must be within societies, society must be within environment. So this sustainable development is actually developed based on the system engineering approach. Okay, basically from system thinking. So we don't want something like this. So this one is actually counter to intragenerational equity. This one. Okay, now we look at the fundamental of chemical looping processes. Just some of them, not too many. Otherwise, I think it will take too long. So let us begin with the basic reaction that we know from our chemistry lessons last time. So let's say we have a carbon that is a solid. We burn that under oxygen, so we produce CO2 gas. Everybody knows about this. This is direct combustion. Also, we can have a carbon monoxide. Okay, we can burn carbon monoxide. Okay, and then we can produce CO2 as well. Direct combustion of hydrogen, again, this is common. I think we did this in the lab last time, many years ago. So we can burn it under hydrogen, under oxygen, then we produce water. Also, similarly, methane is used a lot in the power generation. So methane burn under oxygen that produce CO2 and water. Again, we know about this. Gasification with steam. So we can gasify carbon with steam, then we can produce a mixture of CO and H2. So these two actually we call syngas nowadays. Okay, so we can use this one to produce methanol. Okay, gasification with oxygen. Let's say we have carbon plus oxygen, we can partially burn carbon so that we can produce carbon monoxide. And water gas shift, again, this is very common in the steam methane reforming technology, where we burn CO, where we have a CO react with water or steam that produce CO2 and H2. Okay, this is the basic reaction. Now let us imagine that we have a syngas. It's a mixture of CO and hydrogen. So let's say we burn that, okay, using air so that we can extract the heat. So what we actually produce is a mixture of gas emissions, right? We have CO2, we have nitrogen in the air, we have H2O. So let's say if we want to capture the CO2, so we need to send this one to pressure swing and suction system, PSA. So that can be very costly. So in the way, it's difficult for us to capture CO2 from this gas emission. Okay. Yeah, later we compare that with the other one. This one is we call indirect combustions. So for the combustion, we need oxygen. So here we also can actually get the oxygen from metal oxide. So in this case, right, let's say we have carbon dioxide react with metal oxide, and that can lead to CO2. So the oxygen for here in the metal oxide will be donated to the CO, right, to produce CO2. So now we have a reduction of metal oxide to MOX minus 1. So again, this is a reversible reaction, yeah. And also we can have hydrogen and a gas condition plus MOX. Again, this is solid. Then we can have MOX X minus 1. And then we can have water here. So this is we call indirect combustions. So let us apply this to a specific example. Let's say we burn CO under iron oxide. This one is hematite, Fe2O3. So from that, we can get CO2, and then we get a magnetite, Fe3O4. Or also we can use a copper oxide, mixed with CO. These two will react, that produce CO2, and then we have a copper, a metallic copper, or we can use a nickel oxide, mixed with CO, then we can produce CO2, then we produce metallic nickel. So MOX here is called an oxygen carrier. Long time ago, it was called as a mediator, actually, as a mediator or intermediate. But now I think it's called almost all our thing out there use oxygen carrier for MOX. Now imagine now we have a syngas again, so we want to indirectly burn the CO and H2. Right. So now what we have is that we have a solid OC. The gas emission here consists of CO2 and H2O. So suppose that we want to capture CO2, so we can do that by simple condensation. We don't need a pressure swing and absorption system in this case. We just use a simple condensation. So basically, that is the advantage of this indirect combustion. Okay. Now, chemical looping combustion, let us take a look at the brief history of this. Again, there are so many papers that talk about the history. I think some people start from different era. So here, I think we can go back as far as 1886, okay, where Felix Hope presented a proof of oxygen carrier. Of course, at that time, they didn't mention about oxygen carrier. They call it something else. Okay, but the role or the job of it is still the same anyway, to carry the oxygen, right? So here, the oxygen carrier that Felix mentioned is about the transportation of oxygen via hemoglobin. So hemoglobin here has iron, so that actually attached to the oxygen atoms, right? So hemoglobin actually transport the oxygen to our body, okay, and then the oxygen is used to burn the carbohydrate and other things. So from that, I also still 1886 to 1906, Brin brother used this concept. So now he used a barium oxide principle, okay, barium oxide oxygen carrier for producing oxygen, oxygens. So barium oxide to producing oxygens. Then later, okay, Anton Messerschmitt patented two-stage chemical looping, steam ion process. This one used iron oxide to produce hydrogen. So this method was used to produce hydrogen, and that hydrogen supplied to small industries at that time. Okay, this method remained in use until the discovery of steam methane reforming in the late 1930s. Before steam methane reforming, okay, we used to use this method. Okay, in 1911 to 1930s, something like that. Now, from that, also, we have a pattern, a more serious work now by Gilliland. I think most of us know about Gilliland from the textbooks. So he patented this chemical looping for synthesis gas. Synthesis gas here, we call it syngas nowadays. It's a mixture of carbon dioxide, carbon monoxide, and hydrogens. So the purpose here is to use this the mixture for production of methanol. That pattern was in 1954. Then from there, this technology received more attention. In 1987, Ishida and co-workers introduced a technical term. Now we call chemical looping. Before that, we didn't call it chemical looping. We call it something else. Yeah. So now we call it chemical loopings. And after that formal introductions, what happened in the years that follow? Actually, we have plenty of works that follows after that. For example, Hatono in 1997 that produced the oxygen carrier recycling technology plus this integrated system that he produced. And then Lin and co-workers producing hydrogen under integrated gasification system. Then there's a lot more works that follows after that until now, much more. I think since 20 years ago, there's plenty of works and a number of patents that already filed by researchers in these particular technologies. Okay, that's a brief history. Now, this is again the picture or the diagram for Gilliland pattern. Okay, production of industrial gas comprising carbon monoxide and hydrogen, 1954. Okay. So now moving forward, I think there's a lot more thing to say. So let us cut it short moving forward. So now we have what we are working now at Curtin Universities. Okay, what I'm working now actually since a couple of years ago. We have this idea where we want to design a system based on the chemical looping process to produce hydrogen and also to capture carbon dioxide, and we can also produce power from that. So let me explain here briefly about this system. We have a 3-reactor system. So we call this one moving bed. So chemical looping reaction can be done under 3 different modes. We can use a fixed bed, we can use a moving bed, and the third mode is a fluidized one. Okay, so this one is a moving bed mode. So let us start with the reducer. Okay, in the reducer here, basically we want to reduce the oxygen carriers, right? So to reduce the oxygen carrier, we supply fuel gas. Fuel gas here is a syngas, as a mixture of CO plus H2. Okay. So now we begin with the solid oxygen carrier, which is iron. This one is hematite, Fe2O3 hematite. From hematite, we actually can reduce that to iron oxide and metallic iron. Okay, so here what we produce from this mixture is the CO2 and H2O. Again, we can actually easily separate CO2 from H2O by condensation. Cool it down, and basically we can capture the CO2. And water, here can be basically we condense that, we can get steam or water down here, okay, depending on the temperature of the coolers. Now the next thing, the reduced oxygen carrier is sent to the oxidizer. So how do we produce oxygen, hydrogen? Actually, we produce hydrogen from the oxidizer. So in the oxidizer, we supply steam there, H2O. So steam will be reduced to H2 plus H2O. Again, this one is easy to separate because we can do the condensation method, the applied condensation method, then we can recover the H2, okay? And water can be recycled back to a different system. It could be reused again in this particular reactor. Now, what happened next is that we cannot really oxidize these oxygen carriers directly to the Fe2O3. Okay, so basically most of the time we can only achieve up to Fe3O4. So what we need is that we need a third reactor. We call it combustor. So in the third reactor here, finally we can oxidize Fe2O3, Fe3O4. This is magnetite to the original form, which is hematite, Fe2O3. Now, how can we actually obtain power from this? Actually, for the reducer here, this is could be anothermic, could be exothermic, because there are so many reactions here. Okay, the overall could be anothermic, slightly anothermic, or could be exothermic. For these 2 reactors, these are highly exothermic. So we can extract heat from oxidizer, and also we can extract heat from the combustor. So the heat can be used to produce electricity. Okay, so that is the scheme. So what are the chemical reaction involved? In this case, let's say we use iron oxide and the syngas, okay, as a reaction species for that. So we have 6 reaction, distinct reaction. So that for carbon monoxide, so that react with the iron oxide. Okay, this is hematite, so that produce CO2, then it produce magnetite. From magnetite, it will react again with CO to produce CO2, and iron oxide. Iron oxide react again with CO, and that produce metallic iron. Same thing for hydrogen as well. We have 6 reactions here. So now what we do is that we send this to oxidizer. In the oxidizer, we can recover re-oxidize what they call this one, oxygen carrier using steam. Okay, for example, H2O react with a metallic iron that produce H2, produce FeO. FeO react again with water or steam that produce H2 and magnetite, Fe3O4. Magnetite still can react further. Again, maybe not too much, but actually a little only. It can react with H2O, then that produce H2 plus hematite. Now again, because as we mentioned before, we cannot really oxidize this all the way to Fe2O3. It's impossible, actually, quite difficult, unless we that depends on the design. There's a lot of design. So in many cases, I think we can already achieve up to this point. So what we need to do is that we need to burn it using air so that we can finally get an Fe2O3. And then we can recycle that back to the reducers. So here, this is the two common reaction. Basically, we can accomplish these two steps in the reducer. The last one here actually difficult to get because of the equilibrium case, because this reaction is under equilibrium. Okay, same thing also for the oxidizer. The first two here are quite easy to get. The last one actually difficult to obtain due to the equilibrium limitations. Now, how do we understand this thing? We need to look at the equilibrium phase of iron oxide reduction with CO, CO2, and H2, H2O. So the mixture of these are very important, the ratio of these. Okay. So let us take a look at the first diagram. The reduction here occurs in sequence. We start from hematite. So from hematite, we reduce that to magnetite. Magnetite, then we can reduce that further to wurtzite, which is FeO. From wurtzite, we can reduce it further to metallic iron. So how do we use this phase diagram? So suppose that temperature is here, right? Or let's say 500 degrees Celsius. So if you have hematite, they will move to magnetite. And then from magnetite, it will go all the way to iron. Again, that depends on the composition of CO2 percentage. Let's say 80% CO. So basically, we can get iron. If that is 20%, I think we can get a mixture of magnetite and hematite. Less than that, we can get hematite. Again, that depends on the temperature. Again, if we keep it temperature 500 degrees Celsius here, most probably we just get a magnetite. Now, what we do is that we increase it further at 800 degrees Celsius. Normally, a reducer, the temperature range is between 800 to 1000 degrees Celsius. So basically here, from this, we can reduce it from hematite to magnetite, then go to wurtzite, from wurtzite we go to iron. So let's say average temperature around 900 degrees Celsius. So what we can see here, let's say we actually use CO, right? Consume CO. Now it's become around about 20% CO or 80% CO2. So basically, we cannot go further here unless we need a little bit of magnetite, hematite, then we can reduce the CO all the way to 0. Otherwise, it will stay here. Okay. So the same thing also for the hydrogen. Okay. So now let us take a look at what happened in the oxidizer. Okay, same thing also for the oxidizer. It just reversed that from iron to wurtzite to magnetite, magnetite to hematite. Again, we choose the temperature slightly lower for the reduced oxidizer, around 700 degrees Celsius, actually around 600 to 800 actually. The range, some researchers suggest around 500 to 800. Again, that depends on the oxide that we use. For iron oxide, I think we keep this one around 600 to 700 degrees Celsius. So again, here basically we want to get H2, right? If you want to get a high H2, we need to have an iron there. But if we don't have an iron, so how much H2 that we can get? Let's say we have wurtzite somewhere here, right? So we can get H2 is around 70%. So if we want to increase that further, the oxidation go all the way to magnetite, so we will get less hydrogen. Okay. So again, understanding that phase diagram, I think is quite important when we want to look at how do we set the temperature condition for this particular reactor. Okay. Most of the time, we just get a magnetite and wurtzite only. Okay, we cannot go all the way to hematite, otherwise the hydrogen production is too low in terms of yield of it. So actually, there's a compromise there. Okay, oxygen cleanup, mass heat transfer coupled with reaction. There are three things there. So let's take a look at the shrinking core model. Because suppose that we have a pellet, we can assume this is an oxygen carrier. It takes a spherical pellet. So shrinking core model, basically, if we begin with Fe2O3 here, which is hematite. So basically, this front, right, will be the front of the Fe2O3 will progressively shrink. This one will shrink as the reaction take place from Fe2O3 to Fe3O4. And of course, once we produce Fe3O4, we start to produce also FeO. Once we produce FeO, then we can produce Fe as well. So this is shrinking core model. So basically the core here, basically the region for Fe2O3, okay, that shrink, right, with time. That's why we call shrinking core model. Once this one disappear completely, then we have Fe3O4. Again, that also will shrink with time. So that's why we call shrinking core model. So again, to look at this representation is important when we want to model the oxygen carrier. So again, I will mention again about the oxygen carrier later in terms of modeling of it. The other one is a pellet grain shrinking core model. So we can imagine now within a pellet, okay, we have a small grain, and that grain could be iron oxide grain, right? Could be magnetite, hematite, wustite, or could be a metallic iron. So basically, you have a gas. So basically, this reaction is typically a gas-solid reaction. So the gas has to diffuse into the pellet. Now, once it diffuses to the pellet, they start to have a reaction with the grain here. Again, the grain here can follow the shrinking core model as well, depending. If the grain is small, I think we can assume that the reaction is instantaneous. So basically, the time it takes for the grain to disappear may be too small, right? Nanosecond, for example, we can assume there's almost steady state. But if we take the grain big enough, so it will take some time for the grain to be consumed. So under that condition, we have to use this shrinking core model again for the grain. Before that, we apply shrinking core model for the pellets here, the entire pellet. But now we apply it for the small grain, each one of these one. So this one we call pellet grain shrinking core model. Okay. So how do we describe the mass transfer, heat transfer? We can use those empirical correlation that we find from the textbook actually. So we include it there. So I don't need to explain that. Okay, so here I think the representation of the grain, how do we use that grain, right, to model the system? I think that is an important one when you want to develop a model for this particular system. Okay, now we look at the hydrogen economy. There's a few more aspects there, fundamental aspects. So we just ignore that. We just look at those things only. So let us take a look at the role of that, what it can do in the sustainable development. So for sustainable development, we need an energy transition from currently non-renewable source to the sustainable renewable energy. So as we know, energy is important, right, to power the industry. Without energy, we cannot have the industry. So currently, the industry is driven by fossil-based energy, and that is non-renewable. So the threat to the fossil-based energy issues actually, you can see it into two broad areas. One is source depletion. Basically, this energy can be depleted. Okay, and the other one also you produce greenhouse gas emission. The reason why we need to look at alternative energy because it's depleted. Okay, if we don't have alternative energy, after all of that fossil-based resource depleted, then we cannot run our industry. So our society will collapse then. Okay, again, this one can be simulated actually using there's a what they call it new world. I think there's a new world model developed by Meadow in 1990s, I think. Okay, so you can find actually in the I think you can find there's a link to that where we can use that model to predict the collapse of the resource and those things. Now, the other thing also, even if this fossil-based energy is infinite, right? So we still need to change it over time because it produces greenhouse gas, and that keep increasing our global temperatures. So whatever that is, whether we just look at the source depletion or maybe just look at the GHG, so we need to replace this fossil-based energy sooner or later. Okay. So of course now require energy transition to sustainable and renewable energy. So why we use these two terms? Because not all renewable energy is sustainable. Okay, so here we need to combine these two together. So hopefully the new energy or alternative form of energy that we're going to use to replace this fossil base should be both renewable and sustainable. Hydrogen fuel can be sustainable and renewable. That depend on the methods. How do you produce the hydrogen? We have many different ways to produce hydrogen nowadays. Let's say I think what we use so far, the most common one is the steam methane reforming. Okay, after steam methane reforming, we also have a coal reforming, and then we have electrolysis. By the way, electrolysis only produce about 4% of hydrogen globally, 4% only. And then that is an energy intensive one. The rest of the methods like biohydrogen, thermochemical, water splitting, all those things, these are still under research nowadays. They are not yet entering the commercialization stage. Okay, we look at the three types of hydrogen. The gray hydrogen, this is what we produce now from steam methane reforming. Okay, this is without carbon capture, right? Without carbon capture, we call it gray hydrogens. If we install carbon capture to the system, okay, then we can produce a blue hydrogen, because this one basically we use fossil fuel to produce the hydrogen, but then we have a carbon capture also implement on that system so that we can capture the carbon and then store it. So that blue hydrogen, I think this is also under intensive research nowadays, especially for the power generation one. Now, what I think we are looking at now for future one is the green hydrogen. So green hydrogen here could be produced by water electrolysis using renewable energy, where renewable energy here comes from solar, hydro, or wind. But again, this one is not really efficient. Although, for example, in Sarawak, we have a lot of hydro there. We plan to actually produce green hydrogen. But as you know that to produce hydrogen, right, 1 kilo of hydrogen, we need more energy actually to produce 1 kilo of hydrogen than what it can release if we burns it. So this one is not really efficient. Although we can do it if we have a solar or hydro, but it's not really efficient. So that's why quite a number of researchers now they look at other methods which is more efficient one to produce green hydrogens. So energy for sustainable development have two important criteria. One, it has to be renewables like solar or wind, and then the other one, it should be sustainable. Now, like solar here, right? Some people say solar is renewable, but again, you need to know that the solar is produced to produce solar energy, you need the solar panels. The solar panel require a lot of these rare earth metals, right? So this rare earth metal is not actually it's not renewables anyway. So currently we still have a lot of it, but in future, who knows? Maybe also we have this all of these are depleted. Right? So although it's renewable, but might not be sustainable over the long term. So we need something that's more better than renewables one. So that's why we say sustainables here. So what is sustainable energies? In general, we can say sustainable energy is the one that can meet the dynamic harmony, meaning to say that need appropriate technology. We have a technology to implement it, and also we have a good supply-demand balance. This one must be there. Currently, although we have something that is quite nice, right? But actually, the supply-demand is not there yet. The next one is availability in terms of accessibilities, how easy for us to access it, and whether it's cheap enough or not. So there is affordabilities. And then we look at the energy intensive goods and services. So basically, energy intensive goods and services. So we are actually targeting this area. For example, steel fabrication. This one require a lot of energies. Manufacturing, like cement, for example, that also require a lot of energies, and transportation as well. So we look at the sustainable energy, we're actually targeting certain areas. And then sustainable energy can be accessed by all people, basically intragenerational, the current generation, or intergenerational factors. All of this has to be considered. And future generation, so that one we call intergeneration factors, and preservation of earth also is important. So if we talk about sustainable energy, it must be able to preserve the earth, meaning to say it can address climate change, it can address deforestation, it also can address loss of biodiversities. So again, this is some of the guideline, what we mean by sustainable energies. Okay, green hydrogen and social dimension. I think this from the current review paper by Martins in 2024. So basically here, the authors actually investigate the importance of hydrogens, okay, to the sustainable development goal. We have 17 sustainable development goal, and each of that goal also have a sub goal or sub target, they call it. So the blue one indicate the opportunities of green hydrogen there, the opportunity to implement it or opportunity for it to have a positive impact on that particular target. For example, here, no poverty, right? Then we look at target number 2, number 3, number 4. There's opportunities there. And then also we have a challenge. Opportunity and challenge that exists there. So basically, we need research there, of course, to overcome the challenge and to realize the opportunities. So again, for all of this, we can have some of the opportunities. Also, there's a challenge there. Okay. For the social dimension, this is social dimension number 1, number 2, number 3, 4, 5, 6, 7, 11, and 16. Now we also look at the economic dimension. There is a goal number 8, number 9, number 10, number 12, and 17. So basically here we can have some opportunity as well as the challenge. So what I can summarize here, basically, based on the United Nations 2030 agenda for sustainable development, so we have a roadmap for green hydrogen, okay, in the future energy mix. So here, based on the SDG target, Sustainable Development Goal target, okay, for the hydrogens, you can have 52 opportunities there based on this blue one. Right? We have 52 opportunities, then we can have 47 challenges linked to the SDG with hydrogen. So what we want hydrogen to do for us is that we want to transit, right? There's a transition from the current energy, which is based on fossil fuel, to some to energy which is renewable, sustainable. Meaning to say, we want to shift to the low carbon transitions. So that's one of the role. But again, it should be noted here. Hydrogen is not the only candidate for this. There's other energy as well that can do the same or help. Basically, we need a mixture actually of energy to do this thing. We need hydrogen. We need other mixture, for example, solar, hydro, and so on. There's a mixture. One energy alone cannot do the job. Anyway. It's a big job. Now, for how do we do this? Okay, what we can do for our palm oil industrial, we can turn that into full industrial estate where we can implement this industrial symbiosis. Again, this is an opportunity, just an idea. Yeah. So from palm oil mill, we can produce waste management, right? For example, the empty fruit punch or pomade can be managed, where empty fruit punch and the residue, actually plantation also produce a lot of solid residues that we can actually burn or gasify to produce syngas. From that syngas, we can use that in the chemical looping hydrogen production. Okay, from that we can produce hydrogen there. So again, hydrogen can be used in the and chemical looping. Again, chemical looping can be used for other type of application as well. For example, ammonia production, right? We can use chemical looping as well. So if we have hydrogen, we can use chemical looping and a type of chemical looping to produce ammonia. From ammonia, we can produce fertilizer that can be used in the plantation. Okay. Again, here we can send this hydrogen to hydrogen fuel and energy system. Part of the energy can be transported out. Okay, we can send it to the power grid transmission, or we can sell it out. Part of the fuel can be used by vehicle in the plantation because the plantation will need a lot of vehicles. Okay, so this is an example of the industrial symbiosis. Okay, the role here basically, this hydrogen production can play a significant role that actually link, okay, that make a good links anyway with other type of activities within a particular industrial estate. Okay, currently we just have a palm oil mill only, right? So basically, if we have all of this industry, we can increase the economic potential of industrial estate by 10 times without increasing the size of the industrial estate. So in that way, actually, we can preserve the forest. We don't need to clear more forests, right? So basically, also we can preserve the biodiversities there. We increase the economic potential without increasing the land size. So that is a good benefit in it, actually meeting the sustainable development goals. Okay, what challenge do we have? Again, there are many challenges there. For example, lack of incentive. So we have Paris meeting. This is 2015. I think 2015. There's a typos here. 2015. So again, we haven't translated yet into incentive. Okay, for target reduction emissions. So basically, the lack of incentive, and then we have a limited process understanding. This is an important one. So there's operational uncertainties at large scale. We have a lot of operation at low scale, lab scale or pilot scale, but then we know that if we want to extrapolate the lab scale to commercial scale, I think we can actually meet a disaster there because the process behave differently at different scale, depending on the missing condition and so on and so forth. So we don't know how reactor behave under real conditions. Real condition here basically at the commercial scale. How to effectively control the process to track dynamic goal. So here the dynamic goal involves like the targets, right? The target of hydrogen production, the target of electricity, and so on and so forth. We are not sure how to do that. And then how long oxygen carrier can last on a real large scale operation. Okay, so different oxygen carrier can last with thing under different period. Some can last longer than the others. Some can have a short shelf life. It depends on type of oxygen carrier. So again, there's a risk of investment there. Difficult to scale up the process. This is very complex process involving gas and solids, so it's difficult to scale up. And then we have a lab scale or pilot scale result are not directly we cannot translate it directly to large scale. We need a few more, methodologies there so that we can extend it to the large scale. Again, we have no adequate full-scale plant design. What we have currently is just a pilot scale plant design. Right? We have a few of that, but full-scale plant design is not available yet. Again, why we cannot do that? Because it's too expensive. To initiate something is very expensive one for the full-scale plant design. That is can be costly. A lack of close cooperation between research, society, and industry. So again, we need we need to distribute the knowledge there, the finding from the researchers, and then we need to show the applicability of our findings to the industry. So again, we need a platform. For example, maybe we need a research consortium, for example, where we have active discussion between the researchers and the industrial partners. Currently, I think we are lacking in that area. The lack of mechanism, actually, government support, we need the government support there. Lack of mechanism for financing the process development. The process development for this is very slow. And again, we need more, I think, simulation-based exercise there to speed up the process development. And one crucial thing, oxygen carrier, this is the heart of the chemical looping one, is the oxygen carrier. So we still need to improve the oxygen carrier substantially. Again, attrition, sintering, and agglomerations. And also we can have a carbon deposition depending on the temperature. For example, below 600 degrees Celsius, we can have a Baudot reaction. So basically the reaction will reverse back to the left. So we produce carbon deposition on the oxygen carrier, so that can reduce the effectiveness of the oxygen carriers. So there's a lot of now operating experience here up to date, we have over 11,000 hours operational in total, and then 49 pilots based on for the manufacturer OC experience. This is the manufacturing one. So we have 8,000 hours based on the nickel, mostly based on the nickel oxygen carriers. This one is the most used. So here again, this is report from Anders. Okay, estimated operational experience from 222 publications as follows. Okay, nickel is the most one, the longest one. Then also we have iron oxide. Iron oxide here, I think is average in terms of performance. Nickel is the best one. but nickel is more expensive. Iron oxide is cheap, cheap, and then also widely available. So a lot of people also advocate for this one, including myself. So nickel here is more rare. Actually, maybe we should not use that. Maybe for small scale it's okay. I think for large scale we need to look at something which is more abundance. And then we also have this ilmenite. This is titanium iron oxide. Again, as you can see that the fuel here could be a gas, you see, it could be a syngas or could be a coal as well. Some of them use gas fuel, some of them use a solid fuel like coal. Some use a liquid on kerosene, some of them also use biomass. All sorts of research are happening now, okay, for these particular technologies. There's a lot of research going on. Again, I think we haven't done that much yet in Malaysia. Maybe we can start more to do more works on this one. Okay, for simulation. So simulation here can be done in 3 different ways in broad categories. The first one, which is very common, is steady state simulation. So basically here, researchers try to assess the thermoeconomic and thermodynamics of the thermodynamic properties of the system that they have. Normally they use Aspen Plus. So this one is a steady state simulation. Again, there's a lot of research or report based on for the thermoeconomic and thermodynamic analysis. Dynamic simulation, this is harder to do because we need to have a good model for that. So this one is normally for optimization, control, and operational studies. So if you want to investigate, right, the potential risks of this system and a large scale, we need to have this dynamic simulation. So normally, most of the researchers have to use MATLAB. Some of them use Python to do that. And of course, more complicated, also very complicated one is a computational fluid dynamic simulation. So the target here is to look at the missing effects. Again, we can use this one also for, I think, scale up CFD here. So we look at missing effect using ANSYS Fluence, or the other software that normally use is, I think, COMSOL Multiphysics. These 2 type of packages frequently cited in the articles. Now, for the model, let's say if we look at the dynamic simulation, as this is what I'm doing currently on the dynamic simulation. So we need to have a good model. Not only we have a good model, we need to have a good structure. We need to structure that model, okay, in certain way anyway. It's not that easy. We need to think deep enough about the structure here. Otherwise, it will take a long time for the software or for the computer to solve that. So this one affect the conversion one. And then we need to have a realistic assumption to simplify the model, but at the same time, we still want to produce a reasonable result, okay, realistic result. And then also we need to have a software to solve the differential equation for us. So we can use MATLAB there for dynamic simulation, or you can use a Python one. So MATLAB have a lot of toolbox that we can use. So that's why I prefer MATLAB, because you have a lot of toolboxes there. We have a optimization toolbox, we have a control system toolbox, and many others. So this one is a complete package, although I think we need to start from scratch if we want to use MATLAB. For the Aspen here, I think for steady state is okay. Everything is there already. So we just need to assemble the system, okay, in the Aspen there to analyze it. But for the dynamic simulation, this one is very hard to do. Okay, there's a lot of information that we need to collect and gather, and then we need to arrange them in a systematic ways. So I've done this thing for almost 2 years now, and I'm still compiling it. Okay, what can we do to the oxygen carrier? So basically, we need to model the oxygen carrier. Okay, so to model that, we can use shrinking core model. This is the simplest one, but not so accurate. But I think for exploration, that should be fine. So here we assume uniform progression of the reaction front in a pellet. Now, the one that I'm using now is a pellet grain model, PGM. This is an intermediate one. So we have 3 cases there. It could be reaction limited, diffusion limited, or it could be both. Okay, so basically it's an intermediate in terms of complexities. And then the most complex ones is where we apply the pellet grain shrinking core model. So we have three cases again. Okay, however, in this case, we assume a uniform progression of the reaction front in the grain rather than in the pellets. So we have many grain in the pellet. So this one is more complicated and then take longer time to simulate this one. Okay, this is a sample from the current simulators that I have developed for reducers one. So here we use a fixed bed mode. Syngas flow is 1.5 mole per second. The length of this reactor is about 3 meters, I think. 3 meters. So what we see here is the reduction of oxygen carrier from hematite, right? From hematite, so sequentially to the wustite. We just have a little bit of iron, only metallic iron, but mostly going to the FeO. So again, we have a different zone, meaning to say each of that zone is represented by ODE. Okay, basically the system is under partial differential equation, so we can actually approximate the partial differential equation as a series of ODE. So that's why we have 10 zones in this case. So basically this is the first zone, the inlet one, for the gas. So this is counter current. Counter current, basically gas entering from one side, solid entering from the other side. However, in this case, we just fix the fixed bed, meaning to say the solid is not moved, right? Basically stationary within that particular reactor. So again, we cannot really achieve up to 100%. Normally, we can achieve around 30 to 35% only. Then it's flat. Okay, now here, basically, also we can look at the overall gas conversion because we have two type of gas there. One is CO, the other one H2. So the conversion of the H2 is higher than the conversion of CO. But again, this is still about 95%. I think it should be fine. Again, if you increase this length, the duration of this operation, this one will drop dramatically below. Then actually from 99%, it can drop to 80% within a few minutes only. Okay, now this one is the what they call this one, the reduction of hematites too. So basically hematite here consume a lot in the first zone, then after that also consume in the subsequent zone. Basically what we look here, when we look at zone number 8, right? So it still has significant amount of the hematite here. So again, this is important because if you want to achieve a high conversion using this fixed bed mode, we need to keep this a little bit. Although we want to convert that as actually we want to reduce all the way to iron, metallic iron. That is the ideal case. But if we want to have a reasonable high conversion of the gas, right, we need to keep this a little bit there. Otherwise, our conversion will drop. So again, there's a lot of trade-off that we need to play around there. So that's why we need a simulation to do all of these things. Then after that, we can refine the research using experiments to confirm the discovery. So again, this one is the intermediate one, which is magnetite. Again, magnetite increase first, and after that it drop to 0. Again, because it will be consumed, right, to produce FeO. Okay. Next, we can see again, this is the last one, the iron oxide. So iron oxide increase. So basically, there's a lot of data there. This is just a small fraction of it. So we need again a systematic way. How do we analyze the data so that we can come up with a conclusion, consistent conclusion that can be meaningful to direct the research, further research in the simulation as well as in the experiment. So again, this is a hard work actually. It's not a simple job because we're dealing with a lot of information, and then there's a lot of things that we don't know yet. Everybody's trying to find out the new things, or maybe people try to have a new ideas, but then they still repeat the same information. Depend on how you actually conduct the research. So I think that's why the research in this is still quite slow. But if we focus a little bit more on the simulation, try to build a very good simulation platform, maybe we can speed up the process, the development process. So in summary, we have looked at the chemical looping technologies. We look at the opportunities to produce clean hydrogen, carbon capture and power generation. We look also at hydrogen role, effective role for the transition to low carbon emission. We look at the limiting factors. Limiting factors are quite a lot: lack of incentive, poor knowledge, a large scale operation, difficult scaling up, investment risk, lack of corporations, and a few others. We look also at the simulation. Also, we need to develop a good model and good structure with a realistic assumptions and simulation platform like MATLAB. And finally, we look at CLHP research. It's actually growing rapidly now. In the last 10 years, it grows, I think, has grown a lot. You can see the article produced over the last 10 years. There's a lot. Okay, so the technology is not yet matured. It's still under development. Okay, that's all from me. Thank you for your patience. Okay, any question? Maybe we have one or two questions if you want to ask question. Okay, back to you, Dr. Dini.
All right. Thank you very much, Dr. Jarun. I think very informative and interesting presentation. Previously, I think I heard about chemical looping, but today I just realized what is this is all about. Very, I think complex technology. You can
So
say, right?
technology, yeah, there's a lot of opportunity for research, our research actually, and very useful one because we can apply that to hydrogen production. We can use that for methanol production. We can use it also for the ammonia production. There's a lot more. And also we can use that to reform ethanol and a few other things. And then it is an old technology. The concept is there, been there for over 100 years, but the application are new. A lot of people that try to develop a new application based on this concept, chemical loopings. It's a very interesting one. Yeah.
Okay. 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 Thanks again, Dr. Jarun, for your presentation. So I
You're
would like
welcome.
to
Welcome.
open for the floor, or anyone like to ask question. You can use the chat board, or you can ask
Okay.
directly. Please unmute yourself. Okay. Maybe, Dr. Jerome, maybe I would like to. So in the simulation,
Okay.
you talk about the structure, right? You have to build the structure first. But what do you mean by that? With the structure of your simulation?
Uh, no, actually, when we read the textbook, we have a generic knowledge about the modeling. But what I found
Mhm.
here actually, to solve that conversion, right? Normally, my student last time spent more than 1 year anyway, try to run the simulation in MATLAB, and then it took a long time, and it cannot converge because the
Oh.
dynamic is too complex. So I found that the structure that we use is important. So in my model, I try to arrange a structure so that it becomes self-regulating. When it's self-regulating, you can be sure that the trajectory of that solution will not be negative, because it cannot be negative because this is physical thing. It has to be positive or zero. So I arrange it in such a way so that it becomes self-regulating, so that when we run the simulation, imagine that in the beginning, we don't know the initial value for that. Okay, we're actually guessing the initial value. That's why, the conversion can be very slow because we guess the initial value. So if we arrange it in a self-regulating manner, so it can converge more easily. Okay. So what happened in the papers, they also have that model, but if you guess is wrong, then the value or solution of that can be negative. Then cannot. Then you say, how can the simulation be negative? It cannot be so, right? That is wrong.
Yeah.
Although it solves the problem, okay, the solution is not physically meaningful.
Oh.
So there's a lot of things there, that you need. There's a few tricks. I employ a few tricks to make it work. It,
So
it,
basically,
it is
you
based on my experience.
uh,
Yeah.
okay. So you are like a multi-scale modeling, right? You have like
Yeah. This one is a
yeah.
multi-scale modeling in terms of the size, because you can
Uh-huh.
imagine that pellet is small, right? Compared to the
Yes,
reactor.
very good.
The pellet is about 1 centimeter, let's say, and the reactor, the dimension of it about 1 meter in
Mm.
diameter. So basically, the reactor part of it, the modeling of reactor part is okay. This is standard, not much problem, because
Mm-hmm.
there's no reaction occurring in the reactor. All of the reaction occurring inside the pellet. You see. So the pellet itself is a very complex one. And then if you want to use the most complicated part, let's say the last model just now, right?
Mm.
This one.
The
I haven't tried this
SCM
yet.
combined with pellets, I think.
Yeah. Where is it? Let me see first. This one. I just use this part.
Yes.
Okay. And then this also
Uh,
have a few more assumption there. You have to build in assumption there. I don't want to explain too long, otherwise it will take a long time for us because you just want to get a general idea of it. Now I haven't tried this one yet. This one will need more time to develop this, and then you need a strategy also to implement that on the MATLAB Simulink so that you can solve it. So what we normally do is that we build something from scratch, right? Normally we start from something small first, then after that we gradually build the structure of that
mhm.
simulation. Okay, from a small pallet, okay, we start with one pallet. Okay, in that pallet, actually you can divide it into three compartments. Okay, remember you have three part of that. No, two compartment in that pallet. One is the gas phase. Okay, the gas phase inside the pallet, and also you have a solid phase. Okay, so what we do is that we start first with one of that phase. Okay, not even one pallet yet. Then after that, we start another one with the solid phase. Then after that, once it works, then you combine that solid phase and the gas phase. Then you have a model for one pallet. Then after that, you gradually again combine it with the initially we solve it first for the mass balance. Then after that, we combine it with energy balance. There's a few tricks there just to make it uh,
Mhm.
tractable when you want to simulate it. Again, this is based on experience. I think it's very hard to explain it using textbook. So textbook normally they give you a general what are common things, you know. But when it comes to something like this, you really need experience to build it.
Yes. Yeah.
Yeah,
Okay, thank you very much, Dr. Ron. I think
yeah, yeah.
that's a
Welcome.
very good explanation. So I think we have two questions on the chat.
Yeah.
So first from
Okay, let me
Dr.
check.
Afiq Zubir, how you incorporate the sorbent efficiency into the model because I think conversion drop over the time.
Which one? The simulation.
Uh, I think yes, sorbent efficiency into the model.
Oh, the efficiency for this reduction, right? So basically, we do the calculation. You build a model first in the Simulink. You have a model, a core model. Then after that, the calculation of that, you build another system. Okay, to do the calculation, you attach to it, you know, part by part. All of these things part by part. Actually, there's many components there. So I can show you the things how it look like actually in MATLAB. You know, like just for a while
Oh,
only, just to give an idea. Okay,
okay.
maybe this is not the, the best representation because to do this thing, you need a bit of creative thinking. Okay,
Oh,
okay. Let me show first how to do that one on MATLAB. Yeah. Okay, just a while. Give me a time a bit.
okay, okay, sure, sure.
Okay, okay. Um, document. Okay, so let me share first. So I think I need to share again.
Yes, currently is white space, white
Okay, because that one
space.
is I stopped sharing first, so I need to reshare
Ah,
using the
all right.
screen. Okay. Anyway, there's no secret on my screen, so I don't bother to.
Okay.
Okay, this is the thing. So let's say we
All
open
right.
this one. There's a lot. This one just a fixed bed. Okay. So you need to build a script first. Passionately, you need to build the script for the mass transfer, the heat transfer, the reaction, all of those things, right? You build it gradually, then you can, okay. Okay, this is 10 zone, right? Okay. Let
Okay.
us start from outside first. Okay, this is how it look like. Okay, so you have a this is the palette composition, all those things, the temperatures, the gas stream, pressure, everything here. Design parameter, oxygen carrier
So Dr.
parameter.
Jerome, by the pellet, what do you mean by pellet? The droplet, you
Which
mean?
one? Which
The
one?
pellet, the term you are using pellet. What is the referring to the
Uh,
pellet term actually?
which one palette? Here.
The pellet CP inlet, the pellet and pin.
This
What
the
what is
basic
the pellet
composition.
actually? I'm not clear. What is pellet by you mean? Pellet.
This is the composition of the pellet, because you need to take the composition, for example, here, right? This is the composition of in terms of millimole of hematite. Let's say you start hematite, right? In a pellet, you can actually calculate the initial composition of that pellet. So, and in here, one here basically for hematite. So this one is for the magnetite, wustite, and what they call it, the last one here, basically for the metallic iron. So
Basically,
again,
like a grain, like a pellet,
yeah,
like a
it's a
single
grain. It's
grain.
a grain. That's correct.
Okay.
It's a
All right.
grain.
Okay, okay. Thank you, thank you.
Okay. Actually, I have the document of that Microsoft Docs. Anyway, but anyway, I think just to show you how it works. Okay, this is the thing, right? This is the first zone. This is the last zone. Okay. So in this zone, if you open it, you can see all of these things. Again, we can arrange this thing conveniently because currently I'm still want to produce the structure first. But the rest of those things can be cleaned up easily like, after that.
Mm-hmm.
So you see these things, right? So here you have a zone here. For example, if you look at this is a bulk gas reactor. So how we arrange it, we start from here first. Normally, in my case, I start from this one first, the reaction part, which is in the solid. This is the first one. This this represent the first the compartment, right? Solid compartment in the
Mm.
pellet. And then down here you have a gas compartment. No, the bulk gas. Sorry, wait. I just do this one first. So here, so you have a pellet void. This is the gaseous compartment in that pellet. So you have two compartments in pellet. One is the gas phase. The other one is the solid phase. Then after that, you combine that with the reactor component. So this is reactor mass energy balance here. Okay. So all of these things are repeating. You can use it again. For example, the structure here, right, the same as this one. Once you get that done once, then you can repeat it again and again. You see, the same, the same. And the same thing also intermediate one here, basically, right? You can see this one and the same thing. Okay. So, so that's why I mean, first thing once you get one zone done, then your life will be easy. The next you just combine them. Okay, there's a few tricks how to combine them. But I think that one for other days lah. We can do that other days. And then you can look at the
Okay.
script. There's a script there. You can have a script somewhere. Okay, let me see. First show you the script. This is all the things, right? There's a script. The script, because we need to write a code for that. There's a, let me see for the code. Where is it? Initialization, picture, reducer, report. Okay, this script, right? So that is all the script that you need to write. These are it's not much yet. You still need to add more because you want to include more things. Then you have to add it one by one. Okay, but this is the basic one. Once you got 80% of it, the remaining 20% you can add it slowly, gradually. Okay, so that's why it's the building. This one need time anyway. So that is the script that we use. But again, for this one, there is why we use it because you can include the control later. The problem
Mm-hmm.
with this, if I run this one under counter currents, right, you can have a flat temperature profile in the in the middle of the reactor because there's suddenly you can have a exothermic reaction in the middle there, so the temperature increase beyond 1000 degrees Celsius. That is very hard to control. You cannot really control that temperature. So again, that depends how you actually arrange the reactor configuration. How do you actually design the reactor and also design the oxygen carrier? But I haven't done the study on that yet because we need to set up the model first correctly. Okay. Again, this is still based on the intermediate one, not the most complicated one. So
Mm-hmm.
in the most complicated one, we can build a later version, maybe version 3. This one still version 1. So that's how it look like anyway. Yeah. Is that okay? So
Okay, okay.
basically, right, this one, the other thing also I want to show you is that the currently I show you reducer. You can have oxidizer as well. In the oxidizer, we just combine the reactor. For example, this one, they look like this one, the setting. Okay, this is reducer, this is oxidizer. Okay. Now, why is it the same? Actually, the script of that, both of these, right? You using the same script. Once you build that script correctly, and then you build the basic mode, what do you call the basic simulation correctly, then you can combine it. It's like a building blocks. You need to have the bricks, right, to produce a what I call a building. Once you produce the bricks and a few other things, then you can start to produce a complicated building in the same structure here. Yeah. Now, actually, you can produce again, add a combustor there, then you have complete one. Now I already have a reducer, oxidizer. So next one, just combustor is very easy. It's simple. Okay, the most complicated one is the reducer one. But reducer and oxidizer you can use it together depending on what you feed to it. If you feed the syngas, it become reducer. If you feed the steam to it, it become oxidizer. Okay. Yeah, although it looks scary, but actually it's not that scary after once you know the tricks there. Yeah. All right.
All right. Thank you. Thank you very
Okay.
much for sharing the insight. We
Okay. Okay.
I think there's another one. I think this will be the last question.
Okay.
Dr. Noraini. In your opinion, chemical looping for hydrogen production mature enough to be implemented in Malaysia, maybe by TNB or Sarawak Energy in the near future. What do you think, Dr. Jarrod?
Yeah. Yeah. I think there's some university, there's quite a number of university like Chalmers University. I think already produced the pilot scale one based on the fluidized bed. But again, nobody is there to go to venture into the commercial scale yet, because it's very risky. Everybody is waiting for others to do it. But yeah, we can do that one. And we have a lot of feedstock from palm oil. Palm oil mill produce a lot of the biomass that we can use as a feedstock to this chemical looping. That's why I showed you just now the idea of that symbiosis, in the palm oil mill palm oil estate. We can turn that into a industrial estate using the symbiotic ideas, industrial symbiosis, they call it. So rather than increasing the size of the palm oil estate, we can just keep it the same, just build that symbiosis, then we can increase the economic potential of the palm oil estate 10 times without increasing the size. That way we actually can preserve our jungle, at the same time also preserve our natural biodiversity. Okay. That's what I believe. I think it can be done in the futures, but we need more works to do that. But of course, other people also working at, actually at the end of the day, we have a technology. So maybe next 5 or 10 years, someone really implement a commercial scale. Yeah. Okay.
All right. Okay, thank you, Dr. Jarrod, for your opinion. I think uh, so this is the end of our webinar for today.
Okay.
So before we end, I would like everyone to fill in the what you call feedback form. Okay, so you can refer to your chat box. I already is put a feedback form. So please share your opinion about today's talk. Yes. Okay. So today's talk is brought to you by My PCS. Actually, My PCS is a society made up of lecturers and industrial practitioners that working on process control and process system engineering. So if you are interested to join us, please you can go to our website or maybe contact us. I also okay. So you can also include if you wanted to join as a member My PCS, you can okay do so in using our feedback form. Okay, so today's webinar is recorded. So I will share the recorded. We have Facebook for our Facebook. Okay, and so I think this is just the first our webinar. So I think we are planning to do each month one webinar. So stay tuned for our upcoming webinar. And I just want to highlight, and this year we are also organizing a process control virtual symposium 2026. This is actually like a third edition of our virtual symposium or conference. So you can find more information about this in our website as well. Okay, so again, today we would like to thank Dr. Jobron for his sharing. And okay, so I think that's all for today. Okay, everyone, thank you very much. Okay, so see you in the next seminar or webinar. Right, thank you very much.